Okay, now we finally come to one of the final topics on our discussion of forces, and then we will put everything together, all right? And we're now going to introduce friction. And friction at its root, okay, is a force that opposes the motion of an object. And there are two types of friction, kinetic friction and static friction. So kinetic friction is the friction that acts on an object once it's already moving. So let's say you're pushing a large crate across a floor. Once you get that crate moving, okay, kinetic friction is what's acting between the floor and the crate once it's already moving. Static friction, on the other hand, is the force that's opposing you getting that crate moving in the first place. When you're initially pushing on that crate, before it will move, you have to supply a force that's larger than the static friction force keeping it in place, or else it will not move, okay? Now, technically, I've written equal signs here. These technically should be less than or equal to, okay? So these are technically less than or equal to signs, all right? And what this means is that the force of kinetic friction is going to be less than or equal to this symbol, what we call mu sub k, or the coefficient of kinetic friction in this case, and mu sub s is the coefficient of static friction, times the normal force. Now, friction is a very detailed and very murky subject, but fundamentally it is fairly simple to model, all right? And experiments have shown that these two relationships are very, very good approximations of friction. I put the equal signs in because that's what often we will be using, right? And this means the maximum force that an object can have due to friction, okay? The force of friction, the force of kinetic friction, cannot exceed this product, all right? It cannot exceed this product. But when it is exactly this product, then we use the equal signs, all right? And the same thing goes for the static friction. So what's happening here with this less than or equal to sign, imagine you have that giant crate and it's on a rough concrete floor. And so you start pushing on it with a small force, but that force is less than this product. The force of static friction is only going to be as strong as the force you are putting on it up until you push with this amount of force. Once you push with this amount of force, then the force of static friction is exactly the coefficient times the normal force, and it is at that limit right when you're able to push with this exact force that the crate is in danger of moving. Once you're able to push with a large enough force, then the static friction is in danger of no longer keeping that object from moving. Once you get it moving, then the kinetic friction takes over. Okay, so let me do a real quick example and show you how you can use these. And typically, okay, this is not absolute, but typically your mu values will be between 0 and 1. 0 meaning a very smooth surface, a perfectly smooth surface. Think of an ideal ice skating rink or a hockey rink as having a mu of 0, and then an extremely rough surface will have a mu of 1. And actually, in fact, what's really going on is that each mu is specific to two surfaces rubbing against each other, okay? So I wanted you to make aware of that. So imagine two ice skating rinks sliding on top of each other, okay? That would be a very smooth interaction. That would be a mu of 0. Whereas imagine two rough concrete surfaces grinding against each other, that would be close to a mu of 1, all right? But let's imagine this situation where, let's say that I have a 10 kilogram box and I'm pulling this box across the floor with a force of 20 newtons, okay? So I'm pulling this box across the floor with 20 newtons, but the floor is no longer smooth. The floor now has friction, and so there's a frictional force, and because it's moving, we're going to use the kinetic friction, and the box is sliding along at a constant velocity. So if the box if the box is sliding along at a constant velocity under these conditions, I want to know what the coefficient of the kinetic friction is. Okay, I want to know what the coefficient of kinetic friction is. So how do we do it? Well, the key term here is constant velocity. If I'm moving at a constant velocity, then I have zero acceleration. When I have zero acceleration, then F equals ma is equal to 0, or the sum of all your forces balance. So what that means is that F net, I'm going to define this way to be the positive x direction and this way to be the negative x direction. And that'll put my positive, or the direction that I'm pulling, in the positive direction and friction in the negative direction. Friction, whenever you're moving, again, will always oppose your motion, so it will always act in the opposite direction. Okay, and so this means that I'm going to have 20 newtons acting in the positive x direction minus my force of friction in the negative x direction, and this is going to be equal to 0 because the velocity is constant. Again, anytime you have constant velocity, your acceleration is 0. If acceleration is 0, ma is 0, right? And so now what I can do is say that this 20 newtons is going to equal the force of kinetic friction. And the force of kinetic friction is, of course, less than or equal to mu sub k times n. We will take the equal sign. And so, let me rearrange this. And F sub k is equal to mu sub k times my normal force, and that equals 20 newtons. And so, mu sub k times n, well, remember that n is just the normal force, and in this case, I'm going to have my weight acting downward and the normal force acting upward, and there's no acceleration up or down. So in the vertical direction, F equals ma also equals 0, and what that means is that the normal force is completely balanced out by my weight. And so what that means is that mu k times mg equals 20 newtons. So mu sub k is just going to be 20 newtons divided by mg. All right, so now it's just time to plug in numbers. 20 newtons divided by 10 kilograms. Times 9.8 meters per second squared. And if I divide 20 by 10, that gives me 2. 2 divided by 9.8 gives me 0.204. So mu k in this particular case is 0.204, and again that falls in that range between 0 and 1. So this would be a somewhat smooth surface, but not perfectly smooth surface. All right. Now, one thing I should mention, notice that mu sub k and mu sub s both are unitless. They are just coefficient pure numbers. All right. Here I have newtons, and here I have kilograms times meters per second squared, which is also newtons. So I have newtons divided by newtons, and my final answer is unitless. So the coefficients on your friction values are going to be unitless. Okay, from now on, we're going to be putting all of these together. We'll see you soon.